say ytterbium titanate's true ground state has seemingly been obscured by the sample dependence issue. But now I think it's clear that even in the best quality samples, we don't see conventional behavior. So a lot of the features that some people may have thought were due to the disorder in the samples, I think we can now say are not. So for instance, this continuum of scattering at zero field, I believe, is an intrinsic feature of this material. But one thing that is different is that some samples do order and others do not, or at least develop some ordered moments. And what we've shown is that in what we consider to be the best quality sample, there is an ordered moment of about 0.9 Bohr magnetons that coexists with this odd inelastic scattering. And finally, the inelastic scattering is very similar to ytterbium stanate, so I think it may be important to compare these two materials more closely. And I'd like to conclude by thanking the many people who have helped us get to this point, especially my immediate collaborators, Bruce Boland, Edwin Kermarek, and Jonathan Godet, who were at McMaster University when this work was done. And they were actually the ones who did the inelastic scattering measurements. And at the NCNR, we were very fortunate to work with Juscelino Liao, who helped us deal with this 10-bar helium can thing, which was extremely useful for us to get to the low temperatures. And many other people have helped us along the way, including Lucille and Leon, who are here in the audience. Thank you very much. And I'd like to acknowledge our funding sources, NSERC of Canada, Department of Energy, and Colorado State University. Thank you.
Thanks very much. The paper is open for questions. I notice that. So right there.
Okay, very nice. I mean, it's very interesting. And yeah, let me ask some few questions. And first of all, it's nice to, have some agreement on long-range order, presence of long-range order. It seems that the 0.9 mu B is a little bit, maybe 20% more than the observation in three sample. That's the first comment. And yeah, but then I have a question. So you observed from the diffraction measurement that there's a long-range order. At least 80 Armstrong, longer than 80 Armstrong, right? For the relation.
Yeah.
So then
correlation length.
Yeah. So and the moment is quite large, large enough to see some sharp drop. Steep drop in musar signal, for instance. And usually
in some musar signals, yeah.
Yeah.
Not all of them.
Yeah. So is that the sample, the same sample where you performed the musar experiment and you didn't see the sharp drop of it?
Right. Well, actually, that was a different sample, a different powder sample, and it's a little bit confusing that some musar signals are different from others. So as you know, there has been, the original, I think some of the original interest in this compound was due to the musar experiment that showed a very sharp, I think I have this here. Here. Yeah, so in both ytterbium titanate and ytterbium stanate, there's this first order drop in the spin fluctuation rate, and this seems to indicate some ordering perhaps, but in the original interpretation there was no evidence for a precession in the signal, so it was interpreted as persistent spin fluctuations below this transition. And but then later on there were more musar studies on powders made at McMaster University,